Veronika Hubeny, and she'll talk about CFT probes or bulk geometry.
Okay, thank you, Sunil. Well, it's a great pleasure to be here, and I thank the organizers for the wonderful workshop and for giving me the opportunity to speak. So this is based on two recent papers, one from March and one with Mukund from April this year, set within the ADS CFT context. As you'll see, I'll be firmly in the bulk side of the ADS CFT and in classical geometry. So the plan is to have three sort of separate parts. The first one sort of talking about geometrical properties of various surfaces in the bulk geometry, then focusing on the sort of most interesting aspect of whether we can see or reach inside black holes. And then the third part will be, well, slightly more esoteric, and you'll see what this means when I get there. Okay, so of course I don't need to remind any of you of what ADS CFT is, but the key aspect that sort of motivated the present work was the fact that it maps the sort of gravitational theory into a non-gravitational one, and so one can of course hope to recast all the long-standing questions of quantum gravity in the non-gravitational language and try to answer them on that side. So it has been the sort of information flow between the two sides has of course been going in both directions, and much more so in this direction we are using gravity calculations to understand strongly coupled field theories. But of course there's always the hope at the back of one's mind that one will be able to sort of also use the gauge theory to sort of define and study quantum gravity. But of course to do that we really need to understand very well the dictionary between the two sides, and so part of that goal is what formed the motivation for the present project. So one wants to understand specifically how does geometry, space-time, and therefore gravity emerge from the non-gravitational description, from the CFT. And well, many of the sort of standard quantum gravity questions are somehow rooted on, or the prerequisite to being able to answer them is to understand how does bulk locality come about from the CFT, and of course where does it break down and how specifically does it break down. So as a sort of first step in this direction, one wants to ask, for example, just again within the classical context, so we're at large n and large lambda, within the classical geometry, if you're given a specific bulk location, what quantities in the field theory should one examine in order to sort of understand the physics at that bulk location? Okay, so that's one type of question that we want to sort of gain better understanding of. And a bit more specifically, well, so one can now try to look at various types of CFT quantities, things that I'll call probes, and I'll mention a few particularly nice ones that have a nice geometrical description in the bulk in the moment. But we want to pick these particular quantities, and we then want to ask as a first step, well, how far into the bulk can these specific quantities see in a way? So I'll discuss the geometrical dual, the bulk dual of these CFT probes, and ask where in the bulk geometry these reach. And in particular, a very interesting side of this is, can one see inside a black hole? So of course, because the inside of the black hole is causally disconnected from the boundary, and the CFT in some sense lives on the boundary, one might fear that somehow CFT doesn't know about the inside of the black holes. In fact, that was the sort of original, in the early days of ADS CFT, I think that was the predominant belief. I think by now, most people do think that, including, of course, myself, that you can see inside black holes. In fact, the field theory should contain entire information about the whole bulk. But one can ask, well, are the particularly convenient CFT probes that I will be describing, are those ones which are able to extract information from inside black holes or not? A sort of converse question is not to first pick up a location in the bulk and ask what CFT quantities correspond to it, but rather pick some restricted region in the boundary, in the field theory, some restricted spatial region, and ask, well, what part of the bulk spacetime is that region cognizant of? So if you have, for example, a full knowledge of, say, the reduced density matrix for the field theory on that region, first of all, what bulk region of the spacetime does that fully determine? What the geometry in that region, and what region of the bulk is just sensitive? Is this density matrix sensitive to the bulk geometry rather than explicitly determining it? Okay, so the three parts of the talk will sort of focus on these three questions. Okay, so let me start by specifying what probes I want to be discussing. And basically, I want to concentrate on things that have a nice geometrical description. And in particular, I'll pick essentially just extremal surfaces in the bulk, which are anchored on the boundary. So if you take, for example, the one-dimensional extremal surface, that's just a geodesic, that corresponds to the correlation functions, certain correlation functions. If you pick two-dimensional extremal surface in the bulk, you can relate that to Wilson loop expectation values. If you pick a codimension 2 surface, you can relate that to entanglement entropy, and so forth. So I'm being very schematic here. I'm not going to tell you the precise correspondence. The point is not to actually extract the geometry, for which I would actually have to specify this very precisely, but rather to focus on these geometrical quantities in the bulk and ask, well, what can we learn from them? How far in the bulk do they reach? Okay, so just to remind you maybe a bit of what already has been accomplished in the last decade, I mean, just some cherry picking of the results. So for example, if you consider correlators of high dimension operators and take the insertion on, if you take an eternal black hole and take the insertions on the two asymptotic regions, on the two asymptotic boundaries, so you can think of it as corresponding to operator in one CFT and another operator in another CFT, then that correlator is related to exponential of the mass of the corresponding field times the regularized proper distance along a space-like geodesic that joins these 2 points. So people have used this to try to argue that, well, you can see inside black holes using this way. In 3 dimensions, of course, you can't, these geodesics don't know about the singularity because the spacetime is just purely ADS3. In higher dimensions, that's of course no longer true. And if you look at these space-like geodesics, they bounce off from the singularity and you expect a big divergence in the correlation function. There's a subtlety which rests on the analytic continuation of this, but nevertheless, the upshot of this whole set of works is that these types of correlators are related to space-like geodesics, which are sensitive then to the regions even inside the bulk, even near the black hole. Now, if you don't want to sort of rely on this analyticity, which is a bit of a large constraint, you can consider, for example, things like what we dubbed bulk cone singularities. So if you look at correlators where the insertion points are, well, in the field theory, are separated by a null geodesic, then you have the standard light cone singularity. In the ADS CFT context, actually, this is also true for the insertion points being null separated through the bulk as well as along the boundary. So when the insertion points are separated by a null geodesic through the bulk, the correlator similarly diverges, and we call this a bulk cone singularity. And so knowledge in the CFT of these bulk cone singularities, the locus of these, gives you directly the endpoints of the null geodesics through the bulk, and you can use that in turn to sort of reconstruct the space-time. So for example, if you look, let's just take, say, global ADS. So this is my favorite picture of ADS with time running up, radial coordinate sideways, and here's some angular coordinates. So if you look at null geodesics, let's say projected onto this constant T surface, just slice through this soup can, and projection onto the TR plane. For pure ADS, if you send null geodesics from some point, they all end up on the antipodal point on the sphere, some fixed time pi times the ADS radius later. But if you deform the geometry, so the geometry is not pure ADS but something else, say a star in ADS, then of course these geodesics now feel the gravitational potential well, and so they're going to behave differently from what they would have done in pure ADS. So here's a picture for a particular solution of a star in ADS of what these null geodesics do. They get sort of bent around by the star, and similarly they have the standard time delay when they go through this gravitational potential well. And so knowing the locus of these things, you can invert this, and you can then reconstruct what the bulk metric must have been to cause these endpoints of null geodesics to behave in this particular way. And this has actually been done explicitly for certain symmetric enough spacetimes, so static and spherically symmetric spacetimes. You can do this reconstruction quite explicitly.
But in general, even if you can't do it explicitly, is it clear that you have, I mean, is there a sort of a counting argument which tells you you have enough data to reconstruct it?
So that's a very good question. So that depends again on what all probes you consider. But the short answer is, if you consider enough probes, yes. So already here I have been a bit too glib. So here, since I have looked at just null geodesics, those of course are insensitive to the conformal factor of the bulk geometry. So from just these guys you can't reconstruct the conformal factor. But if you, in addition to this, also include say space-like geodesics, which would correspond to these other probes, then that will reconstruct the conformal factor. So the counting for geodesics would just work. The thing that, so you have endpoints which are constrained to be on a one-dimension lower surface, but on the other hand you have two endpoints, and that always wins. Similarly, if you have a surface on which these, so higher dimensional extremal surface, then you have a full function's worth of freedom of what boundary region that surface is anchored on. And if you take the set of all of these, you have vastly more amount of information than the information contained in the bulk. So naively, the counting would tell you that indeed you always should be able to reconstruct. The snag that might prevent you to reconstruct the spacetime lies mostly in where all can these things reach. So it's clear that if these extremal surfaces can't reach into a certain region of the bulk, then of course you can't use them to reconstruct the spacetime in that region. And that's indeed the focus of this part of the talk. So the going up to from one dimension to the highest dimension, codimension 2 in the full bulk geometry, the dual of the entanglement entropy associated with a certain region was proposed by Ryo and Takayanagi, an area of extremal surface, well, they proposed, they did this in static geometry, so they proposed that the entanglement entropy is related to the area of a minimal surface at a constant time that's anchored on the boundary of that specified region. So as you know, the entanglement entropy is the von Neumann entropy of the reduced density matrix corresponding to this particular region that you choose. And in the bulk, the conjecture is that this is captured by the area of this minimal surface. So when you have time dependence, of course, the minimal surface doesn't have any meaning. I mean, already in Lorentzian geometries, you can decrease the area of a surface just by making it more null. But there's a simple generalization that we discussed in this paper that basically replaces minimal surface with an extremal surface. And you can also think of this, incidentally, as a surface for which the null expansions are zero both in the outgoing and the ingoing direction. So it's analog of the apparent horizon for black holes, but now in both directions, or analog of the bifurcation surface of a black hole, if you will. Okay, so that's the proposal for the holographic entanglement entropy. And again, you can use the knowledge of the entanglement entropy corresponding to a given region to reconstruct what happens in the bulk geometry. So for example, you can study if you have a bulk dual toy model of a thermalization by looking at say a collapsing black hole. So here is a bunch of slices through ADS, again just constant T slices, and you can look at the projection of the extremal surfaces at different times. Now this red circle is the size of the horizon at that time. So if you collapse a black hole, you start from pure ADS and then collapse a black hole in ADS, you can see that these surfaces deform and the corresponding area of them, so pick one of these, say this middle one, and calculate what the area is for each of these times, and you get something that increases like that. Okay, so this is one example. Okay, so that's just to give you a feel for some of the quantities that seem very handy to use for looking at how do we get at a particular region in the bulk from the CFT. So what I'll do is just focus on these quantities for a while and ask what are their sort of features. What can we learn about them?
A question. If the bulk geometry has a non-trivial topology, let's say can CFT's probe say anything about the topology?
Well, I'll discuss a bit in the second part when they have when there's a black hole, so that would correspond to, for example, having two asymptotic regions. But I won't go into more depths with more complicated topologies. But the upshot will be that these probes can probe part of the bulk, but not the full thing. Certainly for static black holes, we'll see that you can't get inside the horizon, so I would guess that for topologically more complicated things, you would have a similar story. Okay.
Sorry, but it's a little different if you have non-trivial topology, right? Because you don't need to get inside anything. You just need to know that there's some hole in this. I mean, if there's a non-trivial topology, you need to just identify a cycle which is somehow non-trivial or something. Right? Seems easier than going inside the horizon.
Well, do we have examples that?
I don't know. Maybe for example, imagine a toroidal direction inside ADS.
Oh, for things like that, then you could for causally non-trivial trivial things, I think you could probe the whole bulk. Yeah, but that certainly is subject to. I mean, one can look at specific cases and discuss those.
So CFT doesn't just give information on local physics necessarily. There's
No, certainly not.
it's
Certainly
capable
not.
of some global
Yes.
structures.
Well, after all, the mapping is very scrambled,
Yeah.
right? So it's certainly very non-local. Okay, so let's start with just geodesics. And for simplicity, let me just take a static and spherically symmetric, asymptotically, globally ADS spacetime, and consider what I'll call probe geodesics, which I'll define to be the ones that have both endpoints on the boundary. And so that means that those can be only the space-like or null geodesics, because the time-like ones never reach the boundary. And we want to consider how deep into the bulk can these probe. So I'll denote that minimal radius by r min. So notice that since we have spherical symmetry, we have a nice geometrical definition of what I mean by the radius. And we can also consider how does their regularized proper length vary, if we want to be sort of going into more detail, for specific sort of separations of the endpoints. So we can ask more and more refined questions in terms of these. The overall question that we're really after is what part of the bulk is accessible to these geodesics, and what are somehow optimal geodesics for getting as deeply into the bulk as possible. So you can of course calculate, you can set up the problem very easily, right? So because of all the symmetries, you can write the geodesics in terms of the radial effective potential, which depends both on the sort of bulk geometry and on the conserved quantities along the geodesics, the energy, angular momentum, and whether it's space-like or null. And you can then describe for a given turning point the separation of the endpoints and the proper length. Now, extracting, sort of inverting this is not as easy because both this minimal radius reached and the separation of the endpoints, of course, depends on, or rather, this minimal radius reach depends on all these parameters as well. And so you can study this in special cases or make very general statements just by looking at the effective potential. So for the easiest special case, of course, is just pure ADS. There we can do everything in closed form very nicely. And you can look at all these geodesics, how they behave, and so forth. So this is what I mean by this angular separation and the temporal separation. But in general, the basic results are the following. So if you have a causally trivial spacetime, of course, the entire bulk is accessible to both space-like and null geodesics. We'll see in the second part that if you have a black hole, then this is no longer true. The geodesics can't penetrate inside the horizon. Now, if you compare space-like and null geodesics for sort of fixed parameters, if you look at this effective potential, then it's clear that if all you're changing is just this parameter, then the effective potential is always lower for space-like geodesics than for null geodesics for the same spacetime and the same parameters. And so that means that you're always better off with the space-like geodesics. That remains true once you fix the endpoints. So for fixed sort of boundary region to which you have access, in which you can anchor your geodesic endpoints, you're always better off with a space-like geodesic than with a null geodesic. And in fact, you're best off with a space-like geodesic with zero energy, one that moves at constant time. And so the optimal geodesics for probing the bulk then are the space-like geodesics that move at constant time. And well, unfortunately, they have the largest proper length, but if you're mostly after how deeply they can probe, then this is the best ones to consider. And so now when I generalize to extremal surfaces, I will no longer consider the analog of the null geodesics, but rather will just anchor my surfaces at some region in the boundary at constant time, spatial region on the boundary at constant time. And so my surfaces in the bulk will also all lie at constant time, the analogs of these E equal to 0 geodesics. So here I'll take again the simplified context. of looking at the extremal surfaces, I'll call them S, anchored on some n-dimensional boundary region rather than say set of 2 points. I can have some finite dimensional region, are in asymptotically ADS geometry, which is both static and is homogeneous around the boundary directions. Okay, so I can describe it by these two functions of the bulk radial coordinate, and since I'm switching to sort of Poincare ADS, I'll now take my boundary at this z equal to 0. The bulk extends to positive z as standard. So the parameters for the simplified context, we still have a lot of things to dial, to study. So we can dial the bulk by these two radial functions. We can dial the shape of this region and its size or extent, which I just define as the sort of the largest, arc, that largest segment that would fit within this region, and the dimensionality of the surface. Okay, that's just a number. So one can then study how these extremal surfaces in the bulk geometry, how do they correspond, how do they respond to changing my region. Okay, and the key thing that we're after is how deep into the bulk do they probe for various modifications of this region. Okay, so the preview of the basic results, or the slogans if you will, is that first of all, the higher the dimension of the surface, the better off you are, the more deeper the surface is probed. Of course, you have to compare them by some quantity, so the most natural thing is to compare them by the extent, because that's always has the same dimension no matter what the dimension of the surface is. Surfaces which are, now if you talk about changing the shape, the surfaces which are anchored on the round ball reach deeper than surfaces which are anchored on any other shape with the same extent or with the same area. And if you deform, if you fix your region and start deforming the bulk spacetime, you're best off in just pure ADS. If you start deforming the spacetime in some physical way, the surfaces are always pushed up towards the boundary. Okay, so those are the upshots of dialing all the things I said we have at our disposal. Okay, so as far as the dimensionality goes, well, you can, this is really hard to see, but okay, so if you consider, for example, anchoring an extremal surface on a strip, but changing the dimensionality of the surface, then you sort of see the profiles change. So a geodesic that would be anchored here and here would look like the semicircle. A two-dimensional surface that would be anchored sort of on this line and this line out of the board would be a bit steeper, because it needs to sort of get to the bulk faster, because it has all this extra, direction where the area is very large, and so forth. The higher the dimension, the quicker it wants to get into the bulk. And you can actually look at the ratio of this extent to the reach, and you see that it increases with the dimensionality of the surface. Now this is a bit of a cheat, of course, because we have, in this picture, we're hiding all these extra directions where this boundary region has infinite extent. So that's not really the best thing to compare with. So the better thing to compare is regions which have, say, a fixed extent. So the most obvious thing is just to compare regions being the n ball for varying n with fixed radius. There you find that in pure ADS, actually, the reach doesn't change at all. They're all hemispherical, so they would all have the same profile as this red curve here that would correspond to the geodesic. But if you start deforming the geometry away from pure ADS, then indeed you do see a separation between the various dimensional surfaces, and you again see the same story as here. So here it is illustrated. I guess you can't see very much for a black hole geometry where the lower dimensional surfaces are the outer ones and the higher dimensional surfaces are sort of slightly further in. Okay, so that's one of the results.
Sorry, what kind of deformation of ADS you consider?
So this particular one was just a black hole. In general, I want something that's what I call physical. What do I mean? Well, one criterion which is sort of easy is that it should satisfy the energy conditions in the bulk. It should produce a physical stress tensor. So if you look at the pressure of the induced stress tensor on the boundary from this bulk deformation, that just knows only about the asymptotic fall off of this. The pressure should be positive as it is for this black hole. So you can see asymptotically that this behavior sort of pans out if you insist on the pressure being positive. Of course, it would go the other way if the pressure were negative, or if you have a negative mass black hole or something like that.
So if I understand, you specify these functions that you wrote there in the metric. So the metric need not solve the
metric need not. Yeah, I should have said that. Thank you. The metric, I'm not assuming any field equations at all, because the whole point was to sort of try to ultimately figure out how you would reconstruct the metric.
So you only require the resulting sort of right-hand side.
I just want them asymptotically ADS, and I'm not even requiring any sort of monotonicity, but for this result, I was requiring them to be physical, and there's a lot that's hidden in that statement that still needs, that would merit much further study.
Excuse me, but all these results you are deducing from the form of that metric you wrote down, it looks like, right? The one you just described.
Indeed. So I have
functions in it, but it seems that CFT doesn't play much role in this reconstruction of space-time.
Well, so one example. One example is you can do a study for what happens sort of asymptotically, and you can write effectively this ratio. There's some formula that you have in terms of the metric functions. You can also figure out in terms of the metric functions what is the boundary stress tensor, and you see that the statement is true. The dimensionality, the higher dimensional surface is reaching deeper, is true, provided the pressure remains positive asymptotically. So that's an input from the CFT. I think there's a much more detailed set of inputs from the CFT which would constrain the behavior of these functions apart from not at the level of solving Einstein's equations, but at the level of certain monotonicity properties of these functions, of their derivatives, and so forth. So for example, we have the C theorem, so that somehow is folded in to constraints on how these bulk functions behave, and I think that in turn would go into sort of making this precise in more generality. So this statement is verified for specific cases like black hole and so forth. It can be shown robustly asymptotically, or it can be shown by taking some specific assumptions that, for example, this metric function is monotonic, but that might be an overkill. So one might be able to relax those assumptions, and that's where the CFT input would be necessary. Okay. So I think it's an interesting direction to explore further, but I'm not going to belabor it because I don't have anything more to say. So now let's turn to what happens if you fix the dimensionality of the surface, anything you want, and look at how changing the shape affects how far these things can, the corresponding extremal surfaces can reach. Okay, so and now we can fix a quantity. We can fix either the extent, or better yet, since they're all same dimensional, we can just fix the area on the boundary of this region we're picking. Okay, so the statement that I previewed for you was that the round ball that would be perfectly circular, is the one that reaches the deepest. Now you already have a guess of that if you compare just the ball and the strip you can show reaches much less deep than the ball, and you might imagine that if you sort of now not take infinite strip but some finite strip, the reach would also be similar, and now you sort of make the strip less and less extended, and the way that this reach changes, you might imagine, is sort of monotonic in your deformation, but that's very hand waving. So another thing that you can do is just analyze this perturbatively by looking at surfaces which are nearly circular. In fact, it will turn out that even these surfaces are sufficiently well approximated to the order that I went in the perturbation theory. So they don't have to be so round, but anyway, we can study this reach in the perturbation theory. Now this is very dense transparency, but the only thing the main point is that that intuition that round surfaces, round regions lead to deepest reach in the bulk pans out. And in fact, you can do this, look at these surfaces, so calculate exactly what these guys look like to second order in perturbation around the hemisphere in a nice closed form where you can get an expression for these surfaces in terms of two free parameters. One, the sort of just an integer parameter, and one, a continuous parameter that sort of describes how these, how many nodes these things have and how sort of much they deform out. Okay, so you see that the area of these, if you fix the reach, the area actually increases with the deformation at second order. And so if you invert that and fix the area, that means that the reach is biggest when the surface is the round sphere. And you can confirm this nonlinearly if you just numerically solve for the surface. Okay, so I'm not going to discuss much the third results that I motivated about this response to deformation of the bulk spacetime, but I'll now move quickly to the statement that none of these can get into horizons. So let me again preview the main points. Well, first of all, if you have some causal probe, like a null geodesic, then of course that by definition can never penetrate an event horizon because it's a causal object. It can't come, or rather, it can't come into the horizon and then come back out and come to the same boundary. But there is no such causal obstruction if you have space-like surfaces a priori, or space-like curves. So you might imagine that our nice space-like extremal surfaces could come happily dip into the horizon and come back out to the boundary. And you might ask, well, can you go all the way, or how far you can go? It actually turns out that if you have a static space-time, you can show that extremal surfaces cannot probe the horizon. You can show this very generally. But if you don't have static space-time, since the event horizon is defined teleologically, in other words, you need to know the full space-time evolution before you can know where the event horizon is, which means that at any given time, you don't have the knowledge, that surface doesn't have the knowledge of where the event horizon is. That means that the space-like surfaces could reach, or in general would reach, inside the horizon. Maybe just a little bit, but nevertheless, there isn't this obstruction that's present for the static spacetimes. Okay, so let me just can't resist sharing with you a very nifty argument for just geodesics in static spacetimes. So suppose you have a geodesic that starts at the boundary and crosses the horizon, and you can ask, well, what happens to it? Well, of course, it can fall into the singularity, but then it's not a probe geodesic anymore, so we don't really want to consider these things. It can go through and come, so this happens if the effective potential sort of doesn't have a turning point. If the effective potential does have a turning point, then clearly the other endpoint must be also on the boundary of ADS. but it could be at the other boundary of ADS. This is in fact the geodesics we have seen plotted at the beginning of the talk. But that's not the probe geodesic we want because it's not anchored on the same boundary. So what we would want is something more like this, where you have a geodesic that comes in, turns around, and comes back out. Incidentally, since I have more dimensions, the fact that this is vertical doesn't mean that it's not space-like because it's just moving in the other directions. So a priori, you might imagine it can do that. But you can see very easily in static spacetimes, you have a conserved quantity along the geodesic corresponding to the energy. And you can see very easily that that quantity, if it's positive for the part of the geodesic which is going inside the horizon, it would have to be negative for the part of the geodesic that goes out. And therefore, you can't have this type of curve either by geodesic either. So this is ruled out. Now, that argument rests on sort of in these coordinates that were valid only here, so that might be circumvented by coming out of the past horizon. But that also can't happen because that would mean that there is a turning point here, and that would have violated the assumption that the geodesic actually made it from the boundary all the way to the horizon in the first place. So the only things that are allowed are these two, but neither of those are probe geodesics. Okay, so for geodesics, it's clear that the probe geodesics can't penetrate the horizon. And you can see it in explicit examples, or rather, you probably can't see it in explicit examples, but well, there's plots of how this geodesic looks for various spacetimes and how close they can get to the horizon. So you can argue that you can get arbitrarily close to the horizon with a space-like geodesic, but at a cost of going around the horizon many times, and therefore forcing the endpoints to be well separated in the angle, if you don't mod out by 2 pi. So if you constrain the geodesic to sort of have endpoints separated by just 2 pi, let's say, then there is some nearest approach to the black hole that such a geodesic would have, some finite number, but it's still a very small number for these specific examples. And of course, null geodesics always reach just a finite distance from the horizon. That corresponds to this unstable circular orbit. That's familiar to all of you. Okay, and that itself also is for infinite separation of the endpoints, but if you fix the endpoints to, again, be separated by some maximally 2 pi, then that minimal reach of null geodesics is slightly above this unstable circular orbit. Okay, so that's for null, for geodesics. You can play the same game for extremal surfaces. So here's an explicit example for Schwarzschild ADS 5 black hole, where I have plotted extremal surfaces of various dimensionalities. So these red curves are geodesics anchored at different separations, n equal to 2 surfaces up to 4-dimensional surfaces. And I have fixed the maximal reach. So you can see that, again, the result from before, that the higher dimensional surfaces would reach deeper for a fixed extent. But you can see, more importantly, that as you get closer to this horizon, these surfaces are sort of repelled. So the ones that would have come all the way to the horizon would hug the horizon forever. In fact, it's interesting to compare what happens for Rice-Nordstrom black hole, where in the standard coordinates you would have this sort of hugging of the horizon much more. But for extremal black hole, the sort of coordinates I was using, the geometrical ones, sort of Pfefferman-Graham coordinates, you would never see the horizon in those. So there's some curious sort of cell similarity in the shape of these surfaces. But you can see that they're all sort of deformed from being what they look like asymptotically. Okay, so maybe in interest of time, I'll just skip the general proof, but I'll just I'll just declare that there is a very simple general proof for any dimensionality, any shape, surface at all, and any bulk geometry, as long as you have a horizon. And so the proof is written in just a few lines, but in interest of time, I'll skip it. But that's the upshot for static black holes. Now for as I said, if you don't have a static geometry, if you have some time-evolving geometry, then surfaces can probe inside the horizon. You can see this already by the very simple argument argued based on teleological properties of the horizon. So in fact, already more than a decade ago, I guess I had sort of this very naive Gedanken experiment of showing that I mean, the causality does not prevent you from, causal obstructions don't prevent you from probing inside event horizon. So you might imagine, take pure ADS, then you have some probe like this geodesic, and after you have done, after this probe, at later time, you can send in a shell that collapses a large black hole, whose horizon actually stretches to the past of where this geodesic went through. Okay, and this is actually explicitly seen in various specific examples. Okay, so let me quickly try to get to the third part of the talk, what Mukund and I called the causal holographic information. Okay, so now we'll sort of stop talking about the extremal surfaces in the bulk, but rather ask the following question. Suppose you have some region on the spatial region on the boundary. I'll now start calling it A. It's a full, for D plus one dimensional bulk, so D-dimensional boundary, it's a D minus one dimensional region. So it's a spatial region covering some finite volume on the boundary. And one wants to ask, given such a boundary region, what is the most natural bulk region that one could associate with this boundary region? Okay, now it sounds very vague to say what is the most natural. Depends what you mean by natural. But essentially, what I want to do is try to be as minimalistic as possible, and I'll try to start by using just causal information in the boundary, not the geometric one. Okay, now. In fact, the causal information actually has most, in some sense, of the geometry. It just doesn't have the conformal factor. But nevertheless, that's the sort of, I'll try to use purely causal constructs to try to do a minimal sort of most natural construction in the bulk that would correspond to this specified region. So what I claim to be this sort of unique minimal construction will correspond to what is called the causal wedge, corresponded or associated with this region. And with this within that causal wedge, I can construct, again, just purely on causal grounds, some preferred surface, D minus one dimensional surface, so same dimensionality as A. And on that surface now I can now take a recourse to geometry and associate a number to that surface, which is simply its area, its proper area, and I'll call that the causal holographic information, abbreviated as chi. And so here are two surfaces, two concepts. One is a surface and one is just a number, which are very natural from the bulk standpoint. And we'll want to ask, well, is there some corresponding feature in the CFT that these things correspond to? In the bulk, they're so natural that one feels like they're bound to have some nice interpretation in the CFT. Okay, so let me first specify the construction a bit more. So just to remind you, the domain of, if you have some region A, the domain of dependence of that region is the set of events that must be influenced by or that must influence this region. So any causal curve from here must necessarily intersect the surface. On the other hand, the domain of influence is a region which can influence or be influenced by that region. So there exists a causal curve that intersects the region. Okay, that's just the definitions. And I'll label the full domain of dependence, so the union of the future and the past domains of independence, by this symbol. Okay, so the question, so one observation is if you know physics, initial conditions, so specifically the reduced density matrix in the field theory, on this region A, then that means that you can automatically, if you know the boundary Hamiltonian, you can evolve, you can automatically determine all of the physics inside the domain of dependence of that region. Okay, so we can determine observables in this entire domain of dependence on the boundary. Now let's try to apply these causal constructions within the bulk. Okay, so here is, so it's again hard to see. So on this side is the boundary, bulk extends in this direction, time goes up, space goes this way. So on t equal to 0, we pick some spatial region A, that's this red line. And if you just associate quantities, causal quantities to that region, like its domain of influence, those things are infinite. If you look at domain of dependence, on the other hand, of this region in the bulk, that's set as 0. So you can't really get some non-trivial, finite, well, finite on this picture set, just from A. But the story changes if now you, instead of A, you consider the domain of dependence of A. Okay, then the domain of influence in the bulk of this boundary region is again infinite. There, the domain of dependence again just collapses onto the boundary, but the intersection of the future domain of influence and the past domain of influence of this boundary domain of dependence is what's called this causal wedge, is on this picture a finite region. Of course, it has infinite volume because it goes all the way to the boundary, but it's a nice sort of what I call a minimal region naturally associated with this A. Okay, so that's the causal wedge. And now on this causal wedge, this is full d plus 1 dimensional volume, space-time volume, but within that space-time volume, you can consider a sort of preferred natural d minus 1 dimensional surface. This is this psi A, which is at the intersection of the sort of past and future boundary of this, or future and past boundary of this causal wedge. Okay, I can define it a bit more carefully, but I guess you know what I mean. Okay, and then to that surface you can associate an area which I call this chi. Okay, so that's the construction. And you can ask what are the properties of this surface and its area. Okay, so in the last 5 minutes I'll try to quickly go through the, just sketch for you the properties. Okay, so this causal, what I call causal information surface, again it's a d minus 1 dimensional surface, which is anchored, of course, on the boundary of our region. In this picture it's just these 2 points. It's one which would reach sort of deepest into the bulk within from all surfaces within the causal wedge. Okay, that's also clear from this picture. It's also a minimal area one among all surfaces that are confined to the boundary of that causal wedge. And, well, in general, it does not penetrate as far as the extremal surface corresponding to A, which are the things that I was talking about in the previous part of the talk. So the picture is the following. So if you have, say, A, region A like this, now this is a global ADS picture, this, suppose the extremal surface corresponding to this region is this green curve here, then this causal information surface, the reach of the causal wedge would reach in general closer to the boundary than the extremal surface. So in particular, if you consider a region and its complement, they of course have the same extremal surface because that one only knows about where the surfaces end, but the causal wedges would differ between the two. So in principle, you would leave some part of the bulk uncovered by the 2 causal wedges. Okay, but so in general, these things are different, But it's interesting to note that they coincide in some special cases, and these special cases happen to be precisely the ones where one is able to compute the entanglement entropy from first principles in the field theory independently of the coupling. Okay. So what are those? Well, they're sort of the trivial cases. You can either have the vacuum, pure ADS, or you can have the thermal density matrix, the black hole, or a rotating black hole. So here I have plotted the causal wedges in global ADS for each of these. So this is what the causal wedge looks like for a region A and its complement that's sort of halfway around the boundary. This is the black hole, so you can see the horizon, the causal wedge is sort of eaten out a bit by the horizon. Again, it's repelled by the horizon even more than the extremal, exactly as the extremal surface. And for rotating BTC, there's even a curious feature that this extremal surface or this coincident causal information surface does not even lie at the same time. Okay, so the property, so you might think, okay, that's great. They coincide with extremal surfaces, and I told you the area of the extremal surface corresponded to the entanglement entropy. So does our chi have anything to do with entropy? The answer is not quite. Well, in these special cases, it does coincide with entanglement entropy, but in general it doesn't, and it diverges much more strongly than entanglement entropy. And it provides a bound, because the surfaces are related to each other, by the way I said before, it provides a bound on the entanglement entropy. But it cannot be an entropy for the crucial reason that it does not satisfy a strong additivity property that is satisfied by the entanglement entropy. Okay, so that you can check in explicit, so it can be easily shown in static spacetimes, as was shown a couple of years ago by Hedrick and Takayanagi. It's a nice geometric proof that entanglement entropy satisfies this strong sub-additivity simply from the features of these extremal surfaces. And recently, Hedrick and collaborators extended it for a special case of Vaidia spacetime just by looking explicitly that this is satisfied. But it is easy to construct counterexamples for this causal holographic information. Okay, so what's the upshot? Well, the upshot is, well, we conjecture that somehow, even though chi is not an entropy, it nevertheless characterizes the amount of information that's contained in this boundary region A that can be then used to reconstruct the bulk geometry. It can do so entirely within this bulk causal wedge, but it should also be able to know of the geometry a bit further, because the extremal surfaces reach further, and as I said, those are also cognizant of the geometry. So there's still a sort of this area under exploration and discussion. What exactly can we fully reconstruct? This is the questions I started out with, and of course, I mean the follow-up, what is the most efficient way of doing so? And what really is the bulk dual of this reduced density matrix? So there have been several recent discussions. Again, in the interest of time, I won't go into that. That are sort of complementary to this story. Okay, so let me then just summarize. So we have seen various properties of these extremal surfaces, and those in general, the thing that reaches the furthest is a highest dimensional extremal surface that's anchored on a round d-1 ball. Okay, in any at least static and homogeneous in boundary directions geometry. I think the symmetry requirements can be relaxed, but then of course you have to define exactly what you mean by a reach and so forth. And we have also looked at what at the same time the extremal surface is not sort of maybe the most minimal natural surface you might imagine because it knows about the bulk geometry. The thing that knows only about the bulk causal structure is the causal wedge, and we conjectured that a number associated with that construction should somehow know about or characterize in some sense the information content that that specified boundary region contains. Okay, so there's many questions that still remain. Most of the things that I started asking at the beginning. So what characterizes the accessible bulk region to extremal surfaces in full generality, the thing that Rajesh sort of asked. How close, now specifically if you have a black hole, we saw you can get a bit into the horizon if the space-time is dynamically evolving sufficiently fast. But how close to the singularity can you actually reach? That still has not been fully examined. What is if you have a specific bulk location, how do we extract the geometry at that point from the CFT data explicitly? And well, given the reduced density matrix, what part of the geometry does that know about, and how do we reconstruct it, and so forth. So since I'm out of time, let me just end there.
Questions?
So sort of a naive question. In the CFT, you could also consider some connected contribution to, say, two disjoint Wilson loops. So sort of two disjoint, the connected piece of that, so that not the factorized piece. So that would presumably be some
it would be some tube that sort of goes between.
Interpolating between two disconnected regions.
Yes.
So would these considerations also apply to disconnected, if you consider several disconnected pieces on the boundary and surfaces interpolating between them, would you also say the same thing, that it cannot penetrate the horizon, etc.?
That's a very good question. Okay, let me think. I guess for that, the general proof that I have was not apply because it doesn't have a turning point. So a priori that could reach into the black hole, but I should think about it a bit more. But I mean, on the other hand, it's not clear that it would.
Yeah, it's not
So,
clear.
I mean, the geodesic, if you
The
sort of think
geodesic
of
doesn't, yeah.
reducing it and
I was
continuing.
thinking that's why of Wilson loops, because they are more non-local.
Yeah, so in some continuation where you reduce each of these to a point
It would
and you
not,
go
yeah.
not from the disconnected factorized branch to but the sort of connected branch, then clearly that wouldn't, because that would just be the geodesic. But if you make these sufficiently large, if you make them too large, then it also wouldn't, because it's more analogous to the story we have seen. But you might just get lucky with some intermediate thing. It's not clear to me, so it's a very good question.
Please. Here.
You're the boss. Yeah.
If you construct the analog of mutual information using your chi, is it positive definite? Does it satisfy the inequalities that it would if you used entanglement entropy?
Well, it certainly doesn't satisfy the strong subadditivity.
Okay, so
I think
so chi in particular, your chi doesn't satisfy subadditivity due to finite terms, not just due to the differences.
yes. I mean, the divergences just cancel out the leading one, right? By definition, but the subleading. So the test case that we looked at was when you have the surfaces anchored on a strip. That it's very easy to see how how the for two sort of overlapping regions like this, strips like this, there you have an explicit expression for the left and right hand side, and you can check very easily that it actually is does not satisfy the. You can find very easy counterexamples.
Okay, so then is the sort of the analog of mutual information even positive definite?
I would say no, but I don't remember. Yeah, I think not.
Sorry, there are lots of questions at the same time. I think I saw Samir first.
Go ahead.
I have another question about this repulsion of extremal surfaces, right? How much does that rely on ADS boundary conditions?
Not very much. So certainly.
Is it true for any space time?
I mean, if you cut ADS, if you have some finite cutoff, that's certainly fine. If you modify the boundary conditions completely, that the extremal surfaces don't really come into the bulk such that they would sort of be near horizon, be sort of dipping down, but then not being able to dip in. If you can't achieve that sort of constellation, then the setup would be different. But I think once you are in the situation where the horizon, where the surface is sort of coming and would want to dip to some distance, but there's a horizon here, then I think it's quite robust to show that its turning point has to lie above the horizon. Yeah. I mean, if you want, I can show you the proof. But
A very humble question. Suppose I consider a free field theory of n scalar fields in 2+1 dimensions. What can that tell us about the bulk theory and its geometry in particular?
I don't think you have any geometry in that case.
Why not?
For free field theory.
Why not?
You need some. You need to have a. I mean, there's a bunch of criteria that the CFT, that a field theory should satisfy to have a bulk dual.
Name one.
It has to have large n. It has to have large gap, and it should be strongly coupled.
But there exists a conjecture, fairly respectable one, I should hope, that this theory corresponds to a rather non-trivial theory of massless higher spins in 4 dimensions. And that has gravitational field in it. But the catch is that there are also infinitely many massless higher spin fields. So then the whole fascinating question of what does one mean by geometry
well, it's also
of higher spin fields.
Yeah, it's a very, very good question, and I would love to know the answer to that.
But there's still geometry, right?
Well, there's not a gauge invariant geometry anymore.
Why not? There's an infinite dimensional gauge symmetry.
Which can then take one geometry and transform it into completely different geometry. In fact, can even get rid of horizons.
I think one needs to define even what's the meaning of higher spin geometry to begin with.
Yeah, I think that's an
So I was deliberately
excellent,
being
fascinating
provocative.
direction, but this has no bearing on that.
Okay, last
Okay,
question.
thank you.
So if you introduce some boundary curvature, like, so does the extent of the depth of the external surface depend on that? Like, if we
Yes. So certainly if you if you
like,
introduce bulk, the boundary with some non-trivial metric,
yes,
of course, then the bulk space-time is modified accordingly. It's not the same space-time because that one also symptotically globally ADS.
so can you use that kind of a construct to always make these two areas, these two surfaces coincide? Like, introduce some sort of boundary curvature so that the external surface coincides with this causal surface.
For different boundary metric.
Yeah.
So you want to take a situation with one boundary metric,
Yeah.
calculate causal wedge, and a completely different boundary metric, calculate
No, I was thinking of the same boundary metric.
same boundary metric. Okay.
But since the extremal area would be different, so maybe there exists.
I see. So you want to just generalize this story to curved boundary metric.
And then maybe, you know, there is a special set of boundary metrics for which it always coincides. And
I would be skeptical just purely intuitively, but it might be interesting anyway to see what effect the boundary curvature would have. My expectation would be that it would still lead to the same relational statements, that the causal wedge is just less deep than these extremal surfaces, blah blah blah, but it would be all slightly deformed.
Okay, let's thank the speaker again.